Okay, hi students, welcome to another video on AEC prerequisites. Okay, this is a video in which we see the working of amplifier. I have considered the same circuit what we have taken in AEC PRE, the last video, which is a voltage divider biasing with R1 R2 connected this way, having the corresponding values, and of course in the solutions also we actually found of course we started with an assumption of VB as 750 millivolts, and we got a current of 91 91 microampere, and upon having a consistency in the different equations of IC has got two equations. One is beta times IB, and other equation is IC is equal to IS exponential VB by VT. So it has to satisfy for both of them. So now in order to make the values of IC satisfying for both the equations, we actually did n number of iterations, and we could able to zero down on the value of IC as almost close to 63 microamperes, and the corresponding VBE is 766 millivolt, and of course this was keeping the BJT in active region. This is keeping the BJT in active region, meaning collector to base junction is reverse biased and emitter to base junction is forward biased. So with these specifications, of course we also verified, so what is the corresponding simulation values of that. Okay, this is the simulation circuit, and we took the same beta factor of 100 and reverse saturation current as 1 into 10 power minus 17. Of course we also verified that, okay, now we can just verify how much is the value of IB. So this is, you can actually add the trace corresponding to, okay, this is IB, which is coming out to be 0.666 microampere. Now this is actually nano. We can actually find out how much is IC. So if you are interested in IC, this is, you can see it's almost 66. So if I write in simulation, the current is 66 microampere, of course 66.6. The VBE comes out to be, if I measure this potential, this is VBE, this is this, so which is 763.7 millivolt, and of course the corresponding value of VC, the corresponding value of VC in the simulation is, okay, this is, okay, let me rerun this, some issue. What I'll do, let me rerun, let me open this, sorry, let me open this, I think it is this one. So I have this, okay, let me slightly read matlab write properly so that you can able to, let me just take a pause now. I'll pause for excuse me. Okay, this is my circuit 170k. Okay, let me name it as R1 as per. Okay, now can sorry. So now how about this? Okay, this is fine. Okay, now this is 80k. Okay, we know that suppose if I run it, okay, take out this, okay, now, or you can do this way. Now this is my IC, which is 66.6 microampere. This is VBE, which is this 763, and the value of VC is 2 point. Okay, what is the value of VC? So in simulation it is, the value is 2.166 volt. So using calculation it is, okay, VCC minus ICRC. So VCC is 2.5. So it is 2.5. This is VC. So IC we are assuming, okay, not assuming, calculation wise it is 63 microampere into 5k. So I mean to say I just want to calculate this value of VC using equations. 2.5 minus 63 exponential minus 6 into 5 exponential 3. So this comes out to be 2.185. So these are all the using equations. So this is using simulation. So they are not too far away. They are very close to each other. Fine. So these are the DC conditions of the MOSFET, which we say that now the amplifier is properly biased. So when I say biased, you are actually fixing the Q point, which will decide what is the IC value and VCE value. So in the output characteristics of the BJT, if this is VCE and IC, if you have this as the characteristics of the the BJT, so there is a corresponding IC, so which is of 66 microampere, and you have a corresponding VCE, which is somewhere here. So this is your Q point. This is the Q point. So which has a particular value of VCE and IC. So this is decided by these resistors and the power supply, and of course the transistor, with the assumption of IS is equal to 1 e power minus 17 and beta is equal to 100, which is as per the simulation also it is so and so. Now let us see the amplifier action. Now to this I need to apply an input. So this is an amplifier having so and so. I need to apply some input. So I need to measure what is V0. So this is what I'm supposed to do now. So this is an amplifier. So this is my input voltage. This is the output voltage. So I have some governing equations. So I know that when I'm applying some input signal, so it will have some amplitude. So now you can see input is applied here. So this is where you are applying the input, and this is where you are measuring the output. So this is where the output is measured, this is where the input is applied. When I say input is applied here, it is always with respect to ground. When I am measuring this output voltage, it's again with respect to ground, because you cannot apply only at one terminal the input voltage, and you cannot measure the output at only one terminal, because voltages are always having two terminals, terminal 1, terminal 2. So one, because when you have any signal coming from either a mic or the output of any radio or output of any sound system, you know that there will be two lines. So those two lines, one has to go to input, other has to go to ground. Even when you want to listen to that, you will have a speaker. Speaker again requires two terminals. So it has got two terminals, one should be connected to ground, other should be connected to output. So this is how it should always have two terminals. When I say input is applied here, it is with respect to ground. When I say output is measured here, it is with respect to ground. So you have two terminals here, you have two terminals here. That's what is this two terminal at the input, two terminals at the output. Now, so what is the voltage that I have here? So the VBE, what you have here is, so let me write what is VBE, and let me also write what is VC. So I am writing what is VB and VC. Let us assume that this is 0, this is also 0. So when you don't apply any input voltage, what was VBE? So let us stick to this theoretical values. VB was 766. So is it okay? 0.76, or let me write as 766 millivolt. So this is my amplitude. Okay, assume that okay till this time. So let us take this as time, this as time. So when you are not applying any input voltage, the voltage at this point is 766 millivolt, because you are not applied anything. So corresponding to this 766 millivolt, will you have a current of this 63 microampere, which is due to, because I know that IC is equal to IS, because of this relation, IC is equal to IS exponential VB by VT with the known value of IS and VT. So IS is how much? 1 into e power minus 17 ampere, and of course VT is 26 millivolt, which we call it as thermal voltage. As I already said in the previous videos, it is KT by Q. It is KT by Q. So corresponding to this IC, do you have a corresponding VC here? Voltage at the collector. Voltage at the collector is how much? It's 2.18. So it is 2.185 volt. So this is the collector voltage, this is the emitter voltage when you don't apply any input signal. So let us assume that to this 766 millivolt VBE, let me apply a input voltage. Now I am applying a very small input voltage of just 5 millivolt. I will apply only 5 millivolt thing. So how much was my VC here? My VC was 5 minus, okay, not 5 minus, 2.5 minus, because VC is given by what equation? I know that VC is equal to VCC minus IC into RC. So what is, this is 2.5 minus 63 micro into 5K. So this is 63 micro when VBE was 766 millivolt. So when VBE changes to 771 millivolt, you can see how it has become 771, because you are applied a 5 millivolt input voltage. When you apply this much, does your IC change? So when your IC changes, does your VC also change? So I need to write the corresponding value of VC for an input voltage of 5 millivolt extra. So now shall I write? I will first find out what is IC is. So how much is IC? So IC is now 1 e power minus 17 into exponential of 771 divided by 26. Can you see the current is now 75 microampere. Corresponding to this 75 microampere, will I have a corresponding voltage? So 75 microampere multiplied by 5 exponential 3 minus of 2.5. 2.5. So this is 2.5. So is this actually 2.122 volt? So you can see what was earlier voltage. Earlier voltage was 2.166 volt. So it was VC was 2.166 volt when you didn't had any V in. So when there was no V in, it was that was 2.166. 2.16 is the simulation value, but calculated value was 2.185. So when I having 5 millivolt extra, so what is this? This is 771 millivolt. Corresponding to this, how much I'm going to have? I'll have it as I'm going to have a voltage which is 2.122 volt. See, when this has increased, this is actually reduced. So let me make it 766 millivolt plus 10 millivolt. So let me apply 10 millivolt extra input. So then what is your IC and VC? So when it was this, IC was I think it was, how much was that? Okay, let me just find out. It was 1 exponential minus 17 into exponential 771 divided by 26. It is my 775.59 microampere is this. When it is 10 millivolt extra, this will become, okay, I'll make it 776 now. It is now 776. So then what will be your IC? Then your IC will be 91.62 microampere. So let me also find out when I have a this is what is the corresponding value of VC. So this into 5 exponential 3 minus of 2.5. Is it not 2.041? This is the value of VC. Can you see when this will become 776? When it is 776, which is 10 millivolt extra, how much is this? This has gone to how much? 2.0. Okay, let me just put this 0 somewhere here. This is not 0, let me put 0 here. So is it not 2.041? See now, when I'm increasing the input voltage, the output voltage is reducing. So now what I'll do, I will make this as 766 minus 5 millivolt. So let me reduce the input voltage, because input can be more than 770. Okay, it can be plus 5 or minus 5 millivolt. I made it minus 5 millivolt. So if it is minus 5 millivolt, is it not, let me find the value of IC. So how much is the value of IC? It is 1, of course I am finding IC using this, 1 exponential minus 17 into exponential, how much is VB? VB is 766 divided by 26, close. You can see now current has reduced to, okay, sorry, I have to make it 761. So this should be 761. So this is 761. Can you see the current is 51.45 microampere. So let me also do it for 766 minus 10 millivolt, so that I can get the value of IC for both of them, which will make my life easy. It is 56 now. Can you see now it is 42.45 microampere. I have these as the currents for a decreased value of VBE due to a negative input voltage, which is minus 5 and minus 10. So what is the corresponding values of VC? So for this it is 5 exponential 3 minus of 2.5. Can you see it is 2.28, and for this it is 2.5 minus minus 51.45 exponential minus 6 into 5 exponential 3. Can you see it is a 2.242. Now see, when the input is, so now this is for positive values. Suppose if I take a value, we have varied the value of this from 766 millivolt. I have added 5 millivolt. It resulted in bit larger input. Okay, because when VB has increased from 766 to 771, IC has increased. Once IC increases, then VC will reduce. So it has reduced to this. That's what is for increase in VB. This VC has reduced. For further increase in VB, VC has further reduced. Now in the next case, we actually reduce the value of VBE by 5 millivolt. It has reduced, but you can see the VC has actually increased from 2.185 to 2. So you can see now it has increased here. So when I reduce it further, here, can you see it has gone to 2.28? So it's actually gone 2.28. Actually, the idea of doing all these discrete values is, of course, we will not be using a discrete value which is going up like this and going up and coming down. Instead of this, we will apply, you can see how it happens. We will apply a sine wave. So on top of this 766 millivolt, I will apply a sine wave. You can see this is how my sine wave is varying. This is a sine wave, how it is varying. With respect to time, it is keep on changing. Let us assume that the amplitude of the sine wave is 10 millivolt. You can see it goes above 10 millivolt from 766, and can you see it goes below 10 millivolt. So when it goes plus 10 millivolt, it is 776. When it goes 10 millivolt down, is it not 756? So what is the peak to peak of your input voltage? Here it is plus 10, another 10 here, it is 20 millivolt peak to peak. This is 20 millivolt peak to peak is your V in. Because of the input voltage is varying around this VBE. So this VBE was your biasing voltage. This is your biasing voltage. On top of this, it is going above and going below. Now, has this resulted in a waveform which is exactly the opposite here? Can you see, when the input is increasing, output is reducing. When the input is reducing, output is increasing. So this is how it is going. It's exactly out of phase. So this is increasing, this is reducing. It is very interesting to see when it is at the maximum peak of 10 millivolt, how much was VC? You can see VC was 2.041 volt. This is 2.041 volt. When it was there at 756, the maximum voltage was 2.28 volt. The collector voltages were, when the input was maximum of 10 millivolt, it was this. When it was minimum at minus 10 millivolt from 766 millivolt, now it has gone here. Shall we see what is the peak to peak of this? Peak to peak of this is the difference of this. So what is the difference of this? You can see it is 2.28 minus 2.041. Can you see now it is almost 234 millivolt. This is the change in the output voltage. How much is the change in the input voltage? It's hardly 20 millivolt. So if I see V in peak to peak, so let me write it here. What is V in peak to peak? V in peak to peak is 20 millivolt, whereas V naught peak to peak is 239 millivolt. Can you see there is a huge increment in the output voltage peak to peak? So this is almost, now I have to find what is the gain of the amplifier. So gain of the amplifier is nothing but AV. We call it as gain of the voltage gain of the amplifier. Usually A is for amplification, V suffix is for voltage amplification, is V naught peak to peak by V in peak to peak. How much is V naught peak to peak? It is 239 millivolt by 20 millivolt. How much is this? It is 239 divided by 20. Can you see the gain is 11.95? 11.95. So this is the gain of the amplifier. This is the gain of the amplifier. Now, what is the entire idea of all these things? Entire idea of all these things is that if you apply a small signal, why you are applying only 10 millivolt? Because we know that the IC is proportional to VB exponentially. Even if this changes by a very small quantity, there is a huge change in the IC value. That IC value will certainly affect your VC. So this is your VC. This is how IC is changing your VC. So now, instead of seeing only 5, 10, so and so, let us apply sine wave in the simulation and try to understand how it happens. Okay, let us go to simulation here. So this is our circuit. This is our circuit. Now to this I have to apply sine wave. So sine wave is there available here. Where is sine wave? So you can see the sources here. Where are the sources? You can go to component. In this component you can see there is a voltage source. So here I need to apply sine wave. So let me connect using wire. Type W, you'll get the wire. Connect this, this and this. Now it is done. Let me apply. Now you go to advanced. Now you are not applying the this one. Now I have to apply sine wave of no DC shift. This DC shift should not be applied. Let me apply a 10 millivolt signal. 10 millivolt signal. Let us take the frequency as around 20 kilohertz. 20 kilohertz. Now I have applied. Okay, let me just move this. Okay, I'm just moving. Now I have applied a sine wave of 10 millivolt peak with a frequency of 20 kilohertz. Now there is no DC signal. Now why there is no DC signal required is because I am already getting a DC voltage due to this R1 R2. This DC should not affect. So if the DC of this should not affect, I have to have a blocking capacitor. So let me connect a capacitor between the input and this biasing circuit. This capacitor blocks the DC of this to reach here, or the DC signal of this should not affect my amplifier circuit. So let me apply 0.1 microampere capacitor. Okay, I'll just move this. Okay, for moving M and then move this, otherwise it just looks okay, fine. So now this is fine. So since the frequency is 20 kilohertz, so I had to assume that you have to see 10 cycles. So what is, okay, let me just show you how to fix this time and all those stuff. So since we have taken frequency as 20 kilohertz, what is the time period for one cycle? Is it not 1 over 20 kilohertz? So what is 1 over 20 kilohertz? It is 20 exponential 3 1 over is. You can see now it is 50 microsecond. If you want to see 10 cycles, what is the time? It is 50 micro into 10, which is 500 microsecond. So my simulation should go from 0 up to 500 microsecond in steps of 1 microsecond. So I can see 10 cycles. So it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's how it look like. So how do you find this final time? Final time is number of cycles, how many you want to see. If you want to see 10 cycles, it is time period into number of cycles. Time period for one cycle is, because this one cycle corresponds to 50 microsecond. So this 10 requires 500 microsecond. So I have to go back here and change this time to, this is 500 micro. This is 500 micro and let it be 1 micro. So now this will guarantee me 10 cycles observation. See now, let me see what is the waveform. Can you see now? You have a waveform. Can you see the input is varying from 0 to 10 millivolt? That's what is here. That's what is here. If you see here, it's actually seeing it here. So let me just tell you what the difference between. Let me just show these two difference. So if you want to see this waveform, where is that? This waveform, which is 766 plus the 10. So this is actually before the capacitor. Since capacitor is blocking this DC, you cannot see that. What I'll do is, let me just show you. So if I measure the waveform here, you can see now. See, I'll put this in different panes. I'll just put it in different panes. So this is one, this is the other one. Can you see this voltage is between 0 to 10 millivolt? Can you see it is 0 to 10 millivolt? How about this? This is a waveform at the base which is actually applied here. Can you see it is 7? Of course, now it is not 766 because the simulation wise it is 7. If you just go back here and try to see in the calculation we took it as 7, it was 766, but in simulation it was 763. So over and above this 763 it varies. So it goes 763 plus 10 is peak, and okay, the minimum is minus 10. So it will go from 763 up to 773 millivolt, and it will go up to 753 millivolt. So again the peak to peak happens to be 20 millivolt. That's what you are seeing here. See here, this is your base voltage. If you actually see it from where it goes, from where to where, you can see this is the peak. Can you see it is 773? This is the least value. Can you see it is 753? Can you see it is 753? So this is peak to peak of your input voltage at the base. This is before the capacitor. So let us observe what is the output. Where to see the output now? Output need to be observed at this point. So let us see the output now. So output is this. So now what I'll do, I will put the output here. Let me just take out this voltage at the base. Okay, let me just take out this input. Let me delete this. Let me put the input here. Now carefully observe. Whenever your input is increasing, can you see the output voltage is reducing? When the input voltage is reducing, can you see the output voltage is increasing? Just zoom it out. See here, the input is increasing, the voltage at the collector is reducing. So when the input is reducing, actually the voltage at the collector is increasing. Now let us see what is the peak to peak of output. So because we already know what is peak to peak of input, so you can see the peak to peak of input, which is 20 millivolt. Obviously, can you see the difference is almost minus 20 because you put the cursor here. Okay, let me put this here and let me put that there. Can you see now the difference is 20, almost there. This is input peak to peak. How much is output peak to peak? See here, output peak to peak is 261. So what is this 261 divided by 20? It's actually 13 is the gain of the amplifier. Of course, in practice or using equations, we got a gain of 11.95, which is almost close to 12. How much in simulation you're getting? You're getting it as 13, of course, which is not too far away from the expected value. So this way, a signal which was of 20 millivolt, you can able to amplify it to 13 times more than that. So now this is how an amplifier works. Suppose if you want to increase the gain of the amplifier, now assume that now you have a gain of hardly 13. I want to get 25, I want to get 100, I want to get 1000, or I want to get 25 as the gain. Is it possible to get? Yes, it is possible to get. a gain of desired quantity, that's what is known as design of amplifier. Design of amplifier. So here we didn't do any design. What we did is, so we earlier had a circuit, to that we applied some input voltage and we were just finding what is the gain of the amplifier. So maybe in the next video we will see why this gain is 12 or 13. How do we theoretically verify or theoretically estimate the gain of the amplifier before we actually verify. So whatever values of R1, R2 and biasing conditions you have, for that biasing conditions, this circuit has to give a gain of 12 or close to 12 or 13, which is not too far away. So that's what is called as design of the amplifier. So if the specification says that you want to get a gain of 25 or 50, I should be designing the circuit in such a way that it gives an amplifier, it gives a gain of so and so. And more than anything, you can see the output voltage is in out of phase with input. So this is increasing, this is reducing. And what is the name of this amplifier? Of course, we say the name of this amplifier is RC coupled amplifier. The name why it is RC coupled is because you are using a capacitor for coupling the input signal and you have a resistor for biasing. So that's why the name of RC coupled. R is this and C is this. So that's what is RC coupled amplifier. But basically the name of this amplifier is slightly different. It is called as common emitter amplifier. So of course you might have studied common base configuration, common emitter configuration, common collector configuration, all those stuff. This is called as common emitter amplifier. So what is the name of this circuit? So name of this amplifier is CE amplifier, which we call it as common emitter amplifier. Why it is called as common emitter amplifier? Let me tell you why it is so. Are you applying the input here with respect to ground? Are you measuring the output voltage here with respect to ground? So do you have one terminal common when you are applying the input or when you are measuring the output? Is this ground is common while measuring the input voltage and while measuring the output voltage? Is this emitter is grounded? Is that emitter is common for both input and output? Yes, note here. Is this emitter grounded here? Since the emitter is grounded and that ground point is common to both input and output, the name comes common emitter amplifier. Emitter is common for both input as well as output. That's why the name of this amplifier is CE amplifier or common emitter amplifier. So this is actually CE amplifier. Right? Okay, we'll explore some other theoretical equation for the CE amplifier in the next video. Thank you.